In the last video we looked at some angular quantities. We're now going to look at two quantities related to circular motion. They are centripetal acceleration and centripetal force. So we'll start by first of all just recalling that in circular motion the direction of the velocity is always changing. And as we know with velocity, that means that when we have a change in velocity, that means that the object is accelerating. And if we consider this scenario that we started out with in the previous video, since the speed doesn't change, that must mean then that the acceleration is in a direction that doesn't cause a change in the speed, only causes a change in the direction. So since the speed doesn't change, it then stands to reason that the acceleration must be perpendicular to the velocity. So if the speed was going to change, some component of the acceleration would have to be in the same direction as the velocity, so that the speed can either increase or decrease. And because we don't see that, we can then reason out that the acceleration must be perpendicular to the velocity. So that then means, if we just have a quick look at a diagram, if we consider the similar scenario that we saw in the last video, if we have a circular path with a mass that's moving with a velocity, in this case to the left, the acceleration would be perpendicular to that, and so it would be directed that way. Now the acceleration is going to cause the velocity to change direction, so at some later point when the object has moved a little bit further, the velocity is now going to be this way. Notice that the size of that velocity is still the same, but the direction has changed. The acceleration will still be perpendicular to the velocity. Then as the object continues to move around a little bit further, the velocity has changed direction again, but again the speed is still constant, so the size of that vector will still be the same, but the acceleration will still be perpendicular to the velocity. Now while this is only a diagram, it does represent something about the acceleration that's important, and hopefully you can see that the acceleration is always directed towards the center of the circular path. So if you think about what's happening in this case, you can see that the velocity is always a tangent to the circle, and if we then have the acceleration being perpendicular to that tangent, then it must mean that it's always directed towards the center of that circular path, and that means it's known as a particular type of acceleration, and it's referred to as centripetal acceleration. That word centripetal, it has Latin roots. I'm not going to go through the Latin roots, but if you want to go and look it up, what you'll see is that it basically can be sort of thought of as a center-seeking acceleration. So the words that make up centripetal in Latin have that sort of meaning of center-seeking. Next thing now that I'm going to do is something that I don't usually prefer to do. Usually I prefer to show you how an equation is derived, but in this case I'm not going to. I'm just going to put the equation in front of you. If you do want to see what the equation for centripetal acceleration is, or how it's derived, you can refer to page 249 and 250 in the text, but in the end we get to the equation A is equal to v squared on r. So that just looks at what happens with an incremental change over a small angle, makes some approximations, and you end up with that equation A is equal to v squared on r. To take that a step further, just going to write the equation down here again, because we'll look at a few ways that we can expand this equation. The first being that if we consider from the previous video that velocity v is equal to the angular velocity omega multiplied by r, so we can write instead that it's omega r squared over r, and if we expand that we get omega squared over r, and so that gives us omega squared r. So there's one form that we can take for that equation, a being equal to v squared on r. On top of that, we also know that omega is equal to 2 pi on t, so 2 pi on the period, so we could square all of that, and then we would get that the equation there becomes 4 pi squared r on t squared. So there's an alternative version that links the radius and the period. So just to summarize the important equations there, a is equal to v squared on r, which is equal to omega squared r, which is also equal to 4 pi squared r on t squared. Now they are the important ones to remember. I don't think the omega squared r is in the data booklet, but I'll just highlight it here anyway, so you can see the link between the acceleration and the angular velocity. One more thing to have a look at in this video, and sort of already identified that we're going to look at the force that's involved. We know from Newton's second law that any time we have an acceleration or a mass, an object of mass m will accelerate when an unbalanced force is applied. Just add the word external there as well, just to identify that it's a force coming from outside the object. So if that's the case, so when we have a force being applied, it's going to cause that mass to accelerate. What it means then, in this case, if a centripetal acceleration is in play, that means then a centripetal force, so a center-seeking force, will cause a centripetal acceleration. And that means that we can use our equation for centripetal acceleration in order to figure out what the force is equal to. So if we think about Newton's second law, F is equal to ma, but we know that the acceleration here is v squared on r, so we can write that instead. So F is equal to mv squared on r. Again, if we go through some of our other ways of expressing v, so omega r, so if we square all of that, divide by r still, we end up then with m omega squared r squared divided by r, and so that then leaves us with m omega squared r. So again, just to highlight the equations that are in the data booklet, F is equal to mv squared on r, which is equal to m omega squared r. So again, we can write the force in terms of the angular velocity rather than the linear velocity. Now, the centripetal force can be provided to an object in a few different ways. We'll have a look at some specific examples in the next video.